So we have learned about these boundary conditions between two magnetic materials. So these are the formulations for the boundary conditions where we have a normal components and we have a normal tangent components formulations. Yeah. Okay, so let's have a look on the examples related to boundary conditions. So for the first example here, we are given the interface 2x plus y equals to 8 between two media which carries no current. Yeah, it carries no current. Mentioned here. If the medium one, which is the region of 2x plus y bigger than 8, is non-magnetic. So non-magnetic means that the permeability is equals to mu naught, yeah, because the mu r equals to 1. And given that the H1 is having a vectors of, there is a magnetic field intensity in medium 1 given by -4 of x plus 3 of y minus z direction. Okay, so this will be the H1 field, yeah, the magnetic field in medium number 1. So if we can sketch it for you, right? So we have the medium number 1 is here. This is the boundary. The boundary equation is given by 2x plus y equals to 8. So 2x plus y bigger than 8 should be the first region. And the second region down here will be 2x plus y less than 8. Yeah. So if we can write the equation, we have 2x plus y less than 8. Yeah. And for the first region, we have 2x plus y bigger than 8. Right. So for the first region, we are given that this is a non-magnetic material. So we have mu equals to mu naught. Yeah, mu equals to mu naught. And there is a H1, which is given by -4 of x plus 3 of y minus z. Yeah? So this is the H field intensity in medium number 1. Okay, so based on these problems, the first one is that you need to find out what should be the magnetic energy density in medium number 1. Okay, this is, if we base on the first question, there is magnetic energy density. Okay, we have learned previously in electrostatic, yeah, electrostatic, if you can recall, in chapter 4, we learned about the electrostatic energy density. If you can recall, we have the equations of WE energy density is equals to a half integrations of d dot E dV. Okay, so this is what we have learned previously in chapter 4, that the energy in electrostatic field is basically given or determined by the field intensity or field density itself, because from this equation we can write that this will be half integrations of epsilon of E squared dV. Yeah, which shows that the electrostatic energy is basically determined by the electric field intensity. Okay, so this is what we have learned previously in chapter 4. So similarly, for the case of magnetic energy density, yeah, we're going to have that for the magnetic energy density, the equation that shall be used in calculating the magnetic energy, Wm, shall be then equals to almost similar to this. So we just change from D to B, yeah, which is the magnetic flux density, and the E field is now changed into H, which is magnetic field intensity. So that should be the magnetic energy that is the formulation, yeah, for magnetic energy that shall be applied, in which we can see that from here the energy or the magnetic energy is basically determined by the magnetic field itself. Yeah, in which from here we're going to have the equation of half integrations of mu h squared dV. Okay, so as I mentioned before, magnetic energy is basically determined by the magnetic field intensity. Yeah, right. So this will be equation will be used in calculating the magnetic energy density in unit number 1, in which for this first part of the question, we can write that the Wm, yeah, because in unit number 1, yeah, so we have half integration. So because mu is mu naught, so we have mu naught, and h squared should be there returned to be 4 squared. Okay, 4 squared plus 3 squared plus 1 squared, yeah, because this is h squared. And we have the dV here, so we can see that the magnetic energy density can be obtained by simply bring the integration of dv to the left hand side. So we're going to have half of mu naught 16 plus 9 will be 25 plus 1 will be 26. So that should be the energy, which is 13 over mu naught joule per meter cube. Okay, so that should be our magnetic energy density in medium number 1. Okay, right. For the second part of the question, which is to find the M2 and B2 in the medium. Number 2, where we have 2x plus y less than 8 with mu2 equals to mu naught. So basically, we have the second medium down here, where we have mu2 equals to 10 of mu naught. Okay, so we need to find out what should be our B2. Yeah, what should be our B2, which is the flux density in number 2, and what should be our M2. That should be the question. Yeah. Right. So let's proceed with the next page here. So let us do it here. So this is your boundary. Yeah, the boundary of the material, which is given by 2x plus y equals to 8. We have the first material up here for the case of mu naught. The permeability is mu naught. Whereas for the second material down here, we have the permeability of 10 mu naught. Yeah, yeah, 10 mu naught here. Okay, so for the H1, it is given by, let me recall, it is negative 4x plus 3y minus z. So we have negative 4x, okay, plus 3y minus z. So your task is to find out what should be the M2 and B2 in the second medium. So basically, we need to find the H2 first. Yeah, need to find the H2 first. So once you find the H2, you can find the M2 and you can find the B2 later on. Yeah. Okay, so this is where we need to apply the boundary conditions. Remember that this particular case, as mentioned here in this question, the medium, the boundary or the interface carries no current, which means that the Js is equals to 0. Yeah, Js equals to 0. So we can write here that Js is equals to 0. Okay, so from here, we can proceed with the calculation of H2. Yeah, remember we need to find the H2. So there are two equations that can be applied or shall be applied. The first one is mu1 of H1n equals to mu2 of H2n, which is for the normal component. Then we have H1t equals to the H1t because the Js is equals to 0. Yeah, so we have two equations here. I label this as equation number 1. This is labeled as equation number 2. Okay, let us proceed with the equation number 1 for normal component. So we have mu1 of H1n equals to mu2 of H2n. Okay, from this diagram, we know that the normal component for this particular case will be this one. Yeah, that should be normal component, whereby if the boundary is 2x plus y equals to 8. So the normal component for this particular surface will be 2 of x plus y divided by z of 5. Yeah, so that should be the normal component. I mean, normally the vector from the surface of 2x plus y equals to 8. So from here, from normal component here, we can use it to find the H1n and the H2n terms. But from here, we're going to have mu1. H1n shall be equals to negative 4 of x plus 3 of y minus z. Okay. All right. And that should be then dot product with the normally the vector, yeah, which is 2x plus y divided by z of 5, and then that should be equal to mu2 of H2n. Yeah. Okay, so knowing that mu1 is mu0, so we just write it as mu0. Okay, and dot product between these two vectors here will give us negative 8 over z of 5 plus 3 over z of 5, and that should be equals to 10 mu0 of H2n. So mu0 can be cancelled out, and end up we are going to have H2n shall be equals to yeah, we're going to have negative 1 divided by 2 z of 5. Yeah, because this will give us negative 5 over z of 5. Yeah, and then we have 10 down here. Then so that will give us 1 over 2 z of 5. Yeah. Okay, so from here, once you get the H2n of negative 1 over 2 z of 5, we can simply write that the H2n vectors, yeah, the h2n vectors, because this is a scalar component or scalar equation. So we can write that the h2n vectors, okay, shall be equals to the h2 dot normal linear vectors. Sorry, my mistake. Sorry, mistake. Yeah. So the h2n vectors, okay, we're going to have it as h2n vectors shall be equal to the h2n magnitude multiplied with the normal linear vector. So that will give us -1 over 2 set of 5 and multiply with the normal linear vector, which is 2 of x plus y over set of 5, and end up we're going to have it as equal to -1 over 5 x direction, and then we have -1 over 10 in the y direction. Yeah, so that should be our h2n vector. Okay, so we have done with the normal component. We have managed to get normal component. So now we're going to find out what should be the h2t by using the second boundary conditions here. So I need to erase few parts. Let me erase this one first, just for us to use the side to solve for the h2t. Yeah. Okay then. So we just write it here that the h2n that we managed to get just now, h2n vectors, will be equals to -1 over 5 x direction minus 1 over 10 of y direction. Yeah. So this I can erase this solution. Okay. So let us proceed with the equation number 2. Okay. So from 2. Okay. From 2. We know that the h1t is equals to h2t. Yeah. Right. So from what we have obtained just now, we can see that the h1t vectors basically shall be equals to the h1 minus the h1n vector. Yeah. And from what we have obtained, that should be -4 of x plus 3 of y minus z direction. And h1n vectors, if we can recall just now, the values for h1n shall be equals to -4 of x plus 3 of y minus z dot product with the an, I mean nominal vector, which is 2 of x plus y over set of 5. Okay, and then this will be then needed to multiply it back with the nominal vector, which will give us 2 of x plus y divided by set of 5. Yeah, right. So end up going to have -4 of x plus 3 of y minus z. Okay, and then to minus it with these values, which will give us -8 over set of 5 plus 3 over set of 5. Then this will be then multiplied with the 2x plus y over set of 5. Yeah. Okay, and from here we're going to have it as -4 of x plus 3 of y minus z minus this will give us -5 over set of 5. So we have 2x plus y over set of 5. Okay, and we're going to have -4 of x plus 3 of y minus z plus, okay, this will be 2 of x, okay, and plus y. Okay, so end up we're going to add the vectors here. So -4x plus 2x will give us -2 of x. 3 of y plus 1y will give us plus 4 of y, and we have -z. So that should be the h1t vectors. Yeah. So h1t vectors is -2x plus 4y minus z. So from 2, yeah. So from 2, we can write that knowing that the h1t is equal to h2t, so we can vectorize. Yeah, we can vectorize this equation here. We're going to get h1t vector shall be equal to h2t vectors. And as such, we can see that the H2T will be similar to H1T, which will give us -2 of x plus 4 of y minus z. So that should be the H2T vectors. And from the H2N that we have obtained earlier, and we have the H2T. So from here, we can find the H2 vector straight away, in which the H2 vector shall be equal to H2N vectors plus the H2T vectors, in which we're going to get it as -2 plus -1/5 of x, which will give us -11/5 of x. Then we have -1/10 of y plus 4 of y, so which will give us plus 39/10 over 10 of y. Okay, and finally we have negative of z. Okay, so that should be our H2 vectors, which has been produced from the boundary conditions 1 and boundary conditions number 2. Okay, so that to be H2. And from here, we can find the B2 and M2, mean the magnetic flux density and the magnetization vector straight away, in which we can see that the B2 will be equals to mu2 of H2, which will give us 10 of mu naught multiplied with H2. And basically, we can also find the M2, whereby we can have that B2 is equals to mu naught of H2 vectors plus the M2 vector. This is from equation that we have seen earlier. So from here, we're going to have the M2 shall be equals to B2 over mu naught minus the H2. Okay, and from what we have here, that B2 is equals to 10 of mu naught. So knowing that the B2 is equals to 10 mu naught of H2 over the mu naught minus H2. Okay, and from here we can say that the M2 can be simply calculated, in which M2 be equals to 9 of H2. Can be cancelled out. So 10 of H2 minus H2 will give us 9 of H2. Okay, so that should be the answer for both B2 and M2. So you can look up for that. Okay then, and finally is to find the angle of H1 and H2 make with a normal to the interface. The angles of H1 and H2 make the normal to the interface. Right, so what is meant by this? Let me erase all of these slides. Okay, so we're going to have this diagram. This is normal. This is okay. This is the first material. This is second material. This is the H1N. The H1 is here, and H2 is here. Okay, this is normal, the interface. The question is, what is the angle that H1 and H2 make the normal to the interface? So the question is to find out what should be the θ1 here and what should be the θ2. Okay, that should be the questions. Okay, so I think this should be very straightforward because previously we have calculated the H1 in terms of their tangent and normal component. For instance, we can write the H1 to be the H1T, and we also have here to be the H2T, right? Sorry, H1N, H1N. Similarly, for H2, we have the H2T, and here we have the H2N. Okay, so basically, the θ1 and θ2 can be calculated by with the help of H1 and H2T, in which from this diagram we can write that the tangent of θ1 can be calculated by simply write the ratio between the H1T and the H1N, in which you need to find out what should be the magnitude for H1T and also for the H1N. Similarly, for the tangent of θ2, we can write that the tangent of θ2 is simply equals to the magnitude of H2T, okay, divided by the magnitude of H2N. Okay, so these are the method of calculating the angle of θ1 and θ2, in which we know that the tangent is a ratio between the magnitude of the H1T and the H1N, and the tangent of θ2 is the ratio between the H2T and the H2N. So from here, we can find what should be the theta 1 and what should be the theta 2, simply by calculating the magnitude of both tangent and normal component for H1 and H2. Okay, so I think you can do it on your own to find out what should be the theta 1 and theta 2 as requested from the question. Okay, so let us proceed to the next examples here. For the next example, we are given these problems whereby there is a first region of given to be in this region x less than 0, and the permeability is 3 mu naught, is separated from the second region of x bigger than 0 and mu2 equals to mu naught by a plane of x equals to 0. So if I can sketch it for you, we have this is the boundary, a plane of x equals to 0. We have the first region, which is x less than 0. So x less than 0 should be down here. This is x less than 0. This is x bigger than 0. So the first region is down here, whereby we have the mu1 is equals to mu3 of mu naught. Okay, and for the second region, which is x less bigger than 0, the mu2 is equals to mu naught. So for the second region, we have mu2 equals to mu naught. Yeah. Okay, so given that magnetic field intensity in the first region is H1, in the first region here we have H1 equals to 10 over mu naught y vector plus z vector. So that should be the H1 vectors. And it's given that the uniform current of Js is 8 over mu naught. Okay, so in this particular case, we are given that there exists the surface current density on this boundary, where the Js is given by 8 over mu naught in the y direction in ampere per meter unit. Conducted on the x equal to 0 surface. So the question is obtain the magnetization vector in the first region. So for the first region, which is down here, I think it should be straightforward. Yeah, because we know that from B equals to mu naught of H plus M, which is also equals to mu of H. Okay, so we can just write that since we know that the mu is 3 mu naught, so that will give us 3 mu naught of H will be equals to mu naught of H plus M. Okay, so mu naught can be cancelled out, and as such, we're going to have the M vector shall be equals to 2 of H. Yeah, 2 of H, and for the first region, we are given the H, which is 10 over mu naught y plus Z. So then we're going to have it as 20 over mu naught of y plus Z in ampere per meter unit for the magnetization vector in the first region. Yeah, so that should be the answer for the first question. Second question is that you need to find out what should be the magnetic field in that intensity and the magnetization vector in the second region. Okay, for second region, we need to find the H field H2. Yeah, we need to find the H2. Okay, so let us use this next page here to answer the question. So let us sketch the problem just now. So this is your problem, the boundary. This is the first material down here. We have mu1 equals to 3 of mu naught. Second region, we have mu2 equals to mu naught. This is x equals to 0. Okay, so we have H1 just now equals to 10 over mu naught y plus z. So mistaken, is it correct? Yeah. Right, and need to find out what should be the H2. What should be the H2? That should be the question. And remember that there is a Js which is equals to 8 over mu naught of y. Yeah? 8 over mu naught of y. Okay. So for this particular case, we know that from this sketching, we're going to have that normal unit vector with regard to the surface will be equals to x direction, yeah, because your surface is x equal to 0. So by right, the normal unit vector should be equals to x. Okay, so from here, we know that there are two boundary conditions to be used, where we have the B1n equals to B2n, or simply it is equals to mu1 of H1n equals to mu2 of H2n. This is the first boundary conditions related to normal component. Then we have the second boundary component. Second boundary condition is that H1T minus H2T equals to JS. Yeah, and what we did now is that we're going to rewrite this in terms of the vector, where we are going to have H1 vector minus H2 vector equals to, sorry, okay, H1 vector cross product, yeah, H1 minus H2 vector cross product with the unit vector of N12, yeah, equals to GS vector. Okay, so this is based on what we have seen previously in the boundary conditions formulations. Yeah, okay, going to use this equation then. Okay, let us proceed with the first boundary condition for normal component. We are given that the H1 is 10 over mu naught y plus z. So from here, we're going to say that the mu1 is 3 of mu naught. The H1n will be then equals to H1 dot n. Okay, and that will be mu2 of H2n. Okay, so we're going to have 3 of mu naught. So H1n is H1 is 10 over mu naught. Yeah, 10 over mu naught y plus z, and normal is in the x direction. Okay, so from here, it's clear to us that the dot product between the H1 and the normal unit vector will give us 0, yeah? In which, from here, we can then say that the H1n is 0. Yeah, the H1n will be equal to 0, and subsequently, the H2n will also equal to 0. Okay, so this is what we can say about the normal component for the vectors, in which from the answers that we get here from the first normal component, yeah, from the first boundary condition, for the normal component, it is stated that the normal component will be 0. Yeah, H2n will be 0. Okay, and for second boundary conditions, which is based on the tangent component, these vectors. Okay, so we given that the H1, yeah, the H1 is basically H1 is 10 over mu naught y plus z, yeah, so we're going to have H1, I can rewrite it here then. Okay, H1 is 10 over mu naught of y plus z. Okay, that should be our H1. Okay, H2 is unknown, yeah, because we don't know what should be the H2. So just write it as equals to H2 x of x component plus H2 y of y component. Sorry. Yeah, H2y of y component plus H2z of z component. Yeah. So because H2 is unknown, so we just put it in general to be H2x of x, H2y of y, and H2z of z. Okay, and we need to cross product, yeah, with the n12, which is a normal unit vector from 1 to 2. So from this diagram, we know that the normal unit vector must be directed from medium 1 to medium 2, in which unit vector should be in this direction, which is n12, which is similar to an. So that should be the x in the vector, yeah. So that should be the x in the vector, and that it should be then equals to gs, which is 8 over mu naught in the y direction. Okay, so for this, we're going to proceed with the subtraction of the vector first inside the bracket. So we're going to have negative h2 of x in the x direction. Okay, plus 10 over mu naught minus h2y of the y in the vector plus 10 over mu naught minus h2z in the z direction. Okay, and this answer from the subtraction, we then cross product the x in the vector, and then it should be then equal to 8 over mu naught of y. Okay, so with this, we can solve for the h2x, h2y, and h2z. Okay, so from here, we can find out that from this solution that the h2x will be 0. Yeah, the h2x will be 0. Yeah, and then you're going to have that 10 over mu naught minus h2y. Yeah, because y cross x will be z. Yeah, y cross x will be z. Yeah, this is Z direction. Okay, plus 10 over mu naught minus H to Z. Okay, Z cross X will be in Y direction, and that should be equals to 8 over mu naught of X. 8 over mu naught in the Y direction. Okay, so from here, when we compare, we're going to have we're going to see that we're going to have that for the Z component, there is no Z component on the right hand side, in which we're going to have that 10 over mu naught minus H to Y to be equals to 0, in which subsequently you're going to have H to Y to be equals to 10 over mu naught. And for the Y component, we have a same similar terms for the Y component, whereby we're going to have 10 over mu naught minus H to Z equals to 8 over mu naught. That's for the Y component. And the solution for that, we're going to have H to Z equals to 2 over mu naught. Okay, so these are the things that we have managed to get. The H to X is 0. This is similar to the normal component just now. And then we're going to have the H to Y equals to 10 over mu naught and H to Z equals to 2 over mu naught. So this will be the replacement, I mean the substitution for the H2 vectors here that we have used earlier, yeah, in which we can write here that the H2 vectors be equals to 0 for the X component, going to have 10 over mu naught for the Y component, and for the Z component going to have 2 over mu naught for the Z component, yeah. Okay, so that should be our H2 that is obtained from the boundary conditions applications. Okay, that should be the H2. And because the question asks us about the H field and also the M2, so the M2 can be obtained straight away, in which the method is similar to what we have seen in the first question just now. Okay, so I think I don't have to do it for you, then you can do it on your own, yeah, for the M2 calculation. Sorry, for the M2 calculation, you can do it on your own, yeah. Right, for the third one, which is to find the energy density in both regions. Okay, so the energy density is similar to what we have discussed in the first example just now. You can use these sections here. Sorry for that. Okay, so for the energy, let's say we proceed with the first region. Yeah, for the first region. For the first region, the Wm shall be equals to half of B dot H dV. Okay, that should be the energy, that's the energy. And we have half, B is mu1 of H, so that should be 3 mu naught. We're going to have 3 mu naught of H squared, okay, dV. Okay, so we can find the energy density by simply bring the ratio, bring the integration to the left-hand side, integration of dV. So that will give us 3 over 2 mu naught in H2 squared, which is just the H squared for the field here. We're going to have it as 100 over mu naught squared times 2. Yeah, let me see. So we have 10 over mu naught for the Y plus 10 over mu naught for the Z. So that will give us 100 over mu naught squared multiplied with 2. Yeah. Okay, so this can be cancelled out. Okay, this can also be cancelled out. So we're going to have 300 over mu naught for the energy in joule per meter cube. Okay, so do the same things. Yeah, you have to do the same things for the energy density in second medium. So for second medium, you're going to have similar techniques to find the energy density. Yeah, because we have obtained the H2 previously from the second part of the question. Okay, so for the second region, the kinetic energy, please do it on your own. Yeah, right. So that should be the end of lecture 19. So for the next lecture 20, we're going to proceed with the topics of inductance, in which you're going to learn about the first part of inductance, which is self-inductance, and followed by the second part, which is the nurturing duct.